Hello, this is Junichiro Horikawa, and this is the 17th episode for VEX for algorithmic design. And the topic today is about intrinsic attributes. And this is the outline for today's sessions. I'm first going to talk about what is intrinsic attributes, then talk about the intrinsic attributes by type of geometries, then talk about some specific intrinsic attributes for primitives like measured area, measured volume, bounds, closed, type ID, and type name. And then I'm also going to talk about some special transform related intrinsic attributes for packed primitive. Now let me first explain what intrinsic attribute is. If you go to a documentation page for side effects Houdini under a geometry attributes, there is a section called intrinsic attributes, and it says intrinsic attributes are computed values derived from the geometry that you can access as if they were attributes. So you can say intrinsic attributes is like a special attributes automatically calculated when you create a geometry. And mainly there's two types of intrinsic attributes. One is for the primitive and one is for the detail. The primitive intrinsic attributes differs based on the types of geometry you're using, like meshes, polygons, nerves, volumes, VDVs, and so on. And detail attributes is more of a global attributes for the geometry, which is for all types of geometries. I personally don't use those intrinsic attributes that much in my workflow, but there are some benefits using them for some purposes for several reasons. So let me explain what those are. Let's start by seeing what type of intrinsic attributes is available for a type of geometries. Okay, so for primitive and detail, so let's start by creating some different types of geometry. First, I'm going to create a grid, set as polygon, and then I'm going to duplicate it and set as mesh. I'm going to duplicate this again and set as nerves. And let me also create a empty volume using volume node, or a VDB node, or like a sphere, set as primitive. And last of all, I'm going to create another grid and then use a pack node to pack this geometry. So let's see those 7 of different types of geometry and what kind of intrinsic attributes are available for them. Now, first of all, let's look at primitive intrinsic for each of the geometry types. So open up the geometry spreadsheet. Then let's select one of the node and let's go to the primitive tab here. Now in default, you don't see any attributes being shown, but actually there is already intrinsic attributes being created for those primitive. And you can check that by going into the drop-down menu called Intrinsics. If you click here, you'll be able to see a list of attributes is available for this geometry type. So for this polygon type geometry, you have a total of 11 primitive intrinsic available. Now, if you click one of the attributes, like measured area, you'll be able to see a bunch of numbers which is available for this primitive attributes, primitive intrinsic attributes for each primitive. Now, if you look at each of the values for these attributes closely, you can actually see these are grayed out, which means these values are read-only, meaning you cannot override this value with different values. But there's also a writable intrinsic attributes like closed. For those attributes which is writable, the text is shown in white compared to these one which is not, which is read only, which are grayed out. These are shown in white text, which is shown it as a writable attributes, meaning you can override the values using VEX code or manually. Now let's check out the other geometry type like grid 2, which was a mesh type. Now if you go there, and there's only one primitive here, and if you click the intrinsic drop down menu, you'll be able to see a lot more attributes types available from compared to the polygon type, like row col or mwrap, vrap. These are the one that was not available for the polygon type, but it's only available for a mesh type. So as you can see, the type of intrinsic attributes available for each primitive is different based on the type of its geometry. If you look at the other geometry type, like for this one, this was a nerves, you have lot more intrinsic attributes available compared to mesh as well. For the volume, you have totally different types of intrinsic attributes like volume, arc value, volume border type, and so on. For the VDB, you've also VDB specific intrinsic attributes like VDB class, VDB creator. For the primitive like sphere, you have a bit less intrinsic attributes available. And for the packed geometry, you have another type of intrinsic attributes like packed full transform or transform, which can be used to create the transformation, do the transformation for this packed geometry, which I'm going to explain the detail about it later for this specific geometry type, a packed geometry. And let's also check for the detail intrinsic as well. If you go to the detail section on the geometry spreadsheet and go to the intrinsic drop-down menu, you'll be able to see a bunch of detail related attributes, intrinsic attributes. And for the detail attributes, the values which is available, the attributes which is available is all the same for all type of geometry. If you click a different type of geometry, you see the same intrinsic values, same detail intrinsic values. So these values, these detail intrinsic values is available for any kind of geometry type. You can access from anywhere. Now that we have looked into a primitive intrinsic attributes for different geometry types as well as detail intrinsic attributes, let's look at some of the primitive intrinsic attributes and detail intrinsic attributes with some examples. Now let's start by looking at some of the basic geometry primitive intrinsic attributes. I'm going to start with the primitive intrinsic attributes called a measured area and measured volume. Now let's bring up a sphere geometry and let's give this to a polygon. Now in most of the cases when I do the algorithmic design using VEX, I use polygon type for the geometry. That is because it's easy to modify using the point wrangle, primitive wrangle. Now changing this to polygon and go back to the geometry spreadsheet, and if you look at the intrinsic drop-down menu, let's check two intrinsic attributes. One is this measured area, and one is called a measured volume. As you can see, for each primitive, this has both of the attributes has some values being created, being already stored. And those are the values that has been automatically calculated when we have created this sphere geometry. And as you can see from the attributes, these are grayed out, so this is a read-only values, which means you cannot override it with other values. Let's create a primitive wrangle first and connect with the sphere. And let's call this measured area. Let's first check how we can retrieve this measured area attribute for the primitive. In order to access to a primitive intrinsic, you can use a specific function called prim intrinsic. So let's try to use this. First, I'm going to create a float a variable like area, named as area, and then use a function called prim intrinsic. Okay, for the parameters, you need 3 parameters. One is the geometry input number, in this case 0, and the second parameter is the intrinsic attribute name. The one that I would like to retrieve now is the measured area and the primitive number, just like when we use prim function to retrieve the primitive attributes. Okay, so first of all, first parameter is 0, and the second parameter is the one that we want to retrieve is measured area. And the primitive number, inside primitive wrangle, we can use this prim num to retrieve each of the primitive number. Now let's have this stored in an attribute so that we can check inside a geometry spreadsheet. So let's create an attribute called area and store this area inside it. Okay, let's go to the geometry spreadsheet, to the primitive, and here is the one that have been transferred from intrinsic measured area, which is right here. So this is how you can access to a primitive intrinsic attribute using this function called prim intrinsic attribute. You just need to check the name of the intrinsic attributes from this drop-down menu like these, and then use it for the second parameter for this function together with the primitive number, and you'll be able to access to its values. Now, some of you might have some questions if there is a measured area available for intrinsic attributes. What's the necessity to have a measure node in Houdini to calculate the area for each primitive? Now let's check what we are going to get by using a measure node to calculate the area. So using measured, connect it to the sphere, and you'll be able to choose the measured area. And for the primitive, and with that option, you'll be able to get exactly the same values as the measured area right here. Now, the benefit of using this measured node is that you can have several options to calculate the area. You can get the total area as well by checking this total attribute name, and be able to add all these area being retrieved or calculated to the detail attribute as a total area. So by using this measure node, you'll be able to have some optional values calculated all together with a basic area attributes. But if you just want to have an area for each primitive and that's all what you need, then accessing to a measured area makes a lot of sense, because since this is already calculated or pre-calculated when you have a sphere being created, you don't actually need to do any calculations when you retrieve this attribute values. In the case of measure node, each time you use the measure node, the area is going to be recalculated using this node. So there is some calculation time going on, meaning if you have tons of polygons to calculate, then this will going to take a lot of time doing it compared to accessing to the already calculated measured area. Now we can actually check the performance using this performance monitor for each the measure node and measured area by accessing to the intrinsic attributes. So I'm gonna try creating the loop feedback loop using for each number node. And let's set the for each end to a feedback each iterations, and for the for each begin, I'm gonna set it to fetch feedback so that this loop becomes the feedback loop. I'm going to connect this sphere into a for each begin. Then let's have this measured node connected in between here. And let's see how much it takes to calculate the measure for tons of times. Now let's calculate this by clicking the record button on the performance monitor page or pane, then go back to the parameter, and let's say we're going to calculate 10,000 times, or maybe 100,000 times. So 10, 100,000, 10,000, 100,000. Okay, and let's see it. By clicking this flag. Okay, now go back to the performance monitor, and it says it took about 6.5 seconds to calculate this measure node, continuing for 100,000 times. Now let's create a similar setup for this measured area. Okay, so I'm going to keep this to the right, and let's delete the measured value and create another for each number. And let's also set this to a feedback each iterations and fetch feedback, connect the sphere. And let's also copy this measured area, and I'm going to just create a f at area and retrieve this measured area from the primitive intrinsic attributes. Connect this one and set the number to 100,000. Before doing that, I'm going to press record, and then okay, 100,000. And if I enter and enable this one, go back to the performance monitor, it says it took around 5.2 seconds. So by accessing to a primitive intrinsic called measured area, it is about 1.5 seconds faster than using the measure node when you repeatedly calculating for 100,000 times. So the difference is not that drastic, but you can see some benefits when you have tons of values to calculate. It might be better using a primitive intrinsic called measured area instead of using a measured node. Now let's also check other primitive intrinsic values, which is called as measured volume. Okay, I'm going to create another sphere, set it as polygon, and this time I'm going to create another primitive wrangle. Now go to the sphere geometry spreadsheet and look at the primitive intrinsic. There is one called measured volume. So this one will give you a volume value for each primitive. And by adding all these values all together, you'll be able to get the volume of this whole geometry. Now let's try to retrieve this one. I'm going to call this measure volume, measure div volume, and then create an attribute called volume and access to a primitive intrinsic by using prim intrinsic function 0 measured volume and at prim num. And let's store this into a attribute called volume. And let's check this out by going into the geometry spreadsheet, and you have just copied the value from the measured intrinsic attribute to a customly created volume attribute. Now having this stored in an attribute, now you can use a node like attribute promote to add all these values, volume attributes values, as a summed up detail attribute. So let's try to do that. The original name is a volume, which is at primitive, and let's promote this into a detail as a sum of the volume attribute values. And don't delete the original. And let's name this to total volume. Okay, now by doing it, you'll be able to add all these attribute values as a total volume into a detail attribute, and this value is going to be the actual volume value for this whole geometry, this whole sphere geometry. Now let's see if we do the same things using a measure node. If we use the measure node for the volume, to calculate the volume, we choose, instead of area, we're going to choose volume. And if you're going to look at the geometry spreadsheet at the primitive, you actually see a different kind of values at each index. The primitive attribute, which is stored in a volume, and the one from the intrinsic measured volume attribute is different. But when you add up all the volumes value you retrieve from the measure node, the actual value you get is actually the same as the one that you have retrieved here. So let's check that out. Going back to the volume measure node parameters and click this total attribute name to have the total volume attribute for the detail, and then go back to the geometry spreadsheet to the detail. You now have this total volume attribute, and the value is 3.658 something. And if you go back here, the actual value you get here is the total volume is actually the same as this one. So even though you have the different values for each of the primitive volume attribute, the sum of this volume is the same. And most of the time, when you use the volume attribute values, you sum up all the primitive values to get the whole total volumes of these of input geometries. So using either way is totally fine. But when you just want to have the total volume, then using measure node might make more sense, because for this one you have to have this attribute promote to add up all the values together. So that was the basic primitive intrinsic values. Let's look at the other values as well. The next intrinsic attributes that I would like to look at is the one called bounds, which is available for both primitive and detail, which is also a read-only values. Now let's check from the primitive bound values first. I'm going to create another sphere geometry. Let's make this a polygon. Now if you make this as a polygon, you'll be able to have a tons of primitive, which is each of these faces. So I'm going to pick one of the face from this sphere using delete node, so that we can focus on one face or one primitive. I'm gonna name this group like a random name here and delete non-selected, so we can just pick one face. By enabling it, this will show you 6 different values, and each of them has this square bracket with the number in it, meaning this is the array value. And since these are expressed in the float values, this is the float array value, which has 6 values inside. And each of the number inside this attributes corresponds to a coordinate value for the minimum position and the maximum position of the boundary of this primitive. The first bounds value means a minimum x coordinate. The second one is the maximum x coordinate, minimum y, minimum z, and maximum z. So let's try retrieving these values using a VEX and try to create a box which covers this primitive as a boundary box to check if these values are really related to the boundary. I'm going to create a primitive rectangle. Let's name this bounds. Let's name this prim bounds. Connect this one. And since we are accessing to a float array, we first going to create a float array variable. Let's name this bounds with a square bracket, which will be expressed as a float array, and then use a same function prim intrinsic coming from the 0 input, the first input. Then the name of the attribute is bounds at prim num. Now by accessing to the bounds value, you should be able to have 6 values contained inside this array. So let's try to access each of the value and use it for its purposes. Now the first index was used for the minimum x, so let's name this min x, and which is bounds 0. And the second value was the max x, so let's name this max x and bounds 1, and do the same for the other 4 values. I'm gonna copy these and rename this to min y, max y, and these to 2 and 3, and 4 and 5 for the z, min z and max z. Now that we have each of the coordinate values, let's try to create 2 vector values, one for the minimum positions and one for the maximum positions. So let's name the minimum positions as min pos, using set to use min x, min y, and min z as a xyz coordinate. Do the same for the max position, set max x, max y, and max z. Now having those 2 vector values, what you can retrieve is a size and the center of this boundary box. Now in order to get the size, what you can do is to just subtract this maximum position with the minimum position will create a size for x, y, and z, which corresponds to max x minus min x for the x size, max y minus min y for the y size, and so on. Okay, so if you want to get the size for the box in the vector value, you can just subtract max pos with min pos. Now in order to get the center position, you just need to add these 2 vectors together and divide it by 2. So vector san pos is equal to min pos plus max pos multiplied by 0.5, equivalent to dividing by 2. Now that we have a 2 informations, let's try to create a point at this center position and apply a vector attribute called scale to its point so that we can use it together with the copy to point node, subnode. Okay, so I'm going to first create a point on the center positions using at point function. Now you should be able to see one single point being created somewhere in the center right here. And then I'm going to set a primitive attribute or a point attribute to this point named as scale, which can be used together with this copy to subnode with attribute size that I have calculated. Now I could also apply some group so that I can only copy the box into the center point. So I'm going to set point group as a center to this point number that I have just created. Okay, so everything is ready. I am going to create a box, which in default the size is 1, 1, 1. So by multiplying this size by scale, should be able to cover this whole triangle by using copy to point subnode. So let's see if this works. Now copy this one And also for the target points, I'm going to check this center so that the box will only copy to the center point right here. If I enable this one, you'll be able to see a box covering the whole triangle. It's a bit hard to see the one inside this box, so let's change this shading to a wireframe. And let's also merge these triangle all together and see how it looks like. And you can see that the triangle is covered by this bounding box correctly. So I think you have successfully retrieved the bounding box from the primitive intrinsic. And also by changing the number of the faces or primitive using for this delete node, in any primitive, you'll be able to cover this. You'll be able to retrieve the bounding values for any kind of primitive. Okay. And if you change this primitive type to something like polygon mesh, it's also the same things, but the shape of the face is a bit different. If you change this to a primitive, you don't see anything. That is because if you look at the intrinsic values, it says -1, 1, -1, 1. So this means some of the primitive doesn't have the correct values for the bounds. So currently we can see that only the polygon or polygon mesh would work. If I change this to mesh, it doesn't have a boundary values anymore. So you gotta be careful that at some of the polygon types or primitive size, you cannot use some of the intrinsic values even though it looks available. Okay, so that's one thing you might need to be careful of. If you are using a polygon, which is going to be the type you're going to use a lot of times, it's not a problem using a bound. If you go to the detail attributes, you can also see intrinsic attributes called bounds. So, and this will give you a similar value as the primitive intrinsic values for the bounds, which gives you 6 numbers in a float array, and this is also used to calculate the bounding box. But this time, the bounding box you get is the bounding box for the whole geometry, the whole sphere geometry. So let's see if that's true. This time I'm going to create a attribute wrangle, and change this to a detail and connect it with the sphere. And this time I'm going to name this detail bounds. Now we're going to do pretty much the same things like I did for the primitive bounds. So I'm going to copy a code that I've wrote for the primitive here and paste it to a detail bounds, a detail wrangle or attribute wrangle, set it as detail roundover. Then one thing that I need to change is this function. This prim intrinsic functions only works for the primitive intrinsic value, but in order to get the detail intrinsic values, you need to use a different function, which is called as detail intrinsic. Okay, and for this one, you just need to have two values, two parameters, which one is the input geometry number and the intrinsic name. So in this case, 0 and bounds. And as a result, you'll be able to get the same float array. And go down and If I enable this, you should be able to see a new point being created as a group named as center. So let's check that out. Going to a point wrangle, and you should be able to see one point being created as a center, which contains the scale attributes. Okay, so let's try to use this one using the same setup right here. So I'm going to copy this one right here and connect this to the second input of this copy 2 points, and connect this one to the merge and delete this one. If I show this up, you see that this sphere now is covered with this bounding box. So if you want to have the whole bounding box information, you can also use this detail attribute, detail intrinsic attributes. Although there is a function in VEX to get the bounding box information, especially for the size and the center position and the minimum and maximum as a vector value, like get bbox or get bbox_min and so on. So you don't actually need to, most of the case, you don't use these bound primitive or detail intrinsic values. If you need to access a specific coordinate like the minimum x coordinate or minimum y coordinate or maximum z coordinate, then accessing to a primitive or detail intrinsic values might make sense, but most of the cases using VEX function like get bbox would just do the job for you. But it is useful for the primitive intrinsic. I mean, most of the cases when you use the get bbox in VEX functions, what the result you get is same as the one used for the detail bounds. But for the primitive bound, if you want to get the bounding box for each primitive, then using primitive intrinsic bounds might be really useful. You can do the same things using get bbox by applying setting the optional parameter like the primitive group, but this primitive intrinsic bounds can be accessed without setting without those group setup. So it might be a bit faster, but most of the case, VEX function just works just fine. Now I would like to talk about other type of primitive intrinsic values, which is called as closed. This closed attribute is a bit special compared to the other intrinsic attributes because it is writable. So you can override the values to change the behavior of the geometry. So let's see what kind of behavior we could see by changing the values. So this closed attribute is probably only available for the polygon type primitive. So I'm going to create another sphere and set it as polygon, and go to the, let's change the shading back to the smooth wire shaded, and then go to the geometry spreadsheet to the primitive tab. Let's hide all these primitive intrinsic and show only this closed primitive intrinsic. Now it shows the values, the integer values 1 for all the primitive values, and this indicates whether this primitive is closed or not. If it's 1, then each primitive is closed. If it's 0, then that means each primitive is not closed. So currently all the faces, all the primitive face is being closed, so all the values is equal to 1. But if I use a node like primitive and make each of the face open by going to the face hull and change the close U to open, and go back to the primitive attribute, you see that all the closed intrinsic closed attribute become 0. So you can indicate each of the values. You can check each of the values to indicate whether the polygon is closed or not. As you can see, if you look at the attributes, these values are not grayed out, meaning it is writable. So you can actually modify these values using a VEX code to make it open again or closed back again by setting the integer value 0 or 1 to each primitive. So let's try to do that. In between the sphere and the primitive node, I'm going to create a primitive wrangle. Okay. And I'm going to create a random values like using rand with a p as a seed. And then make a condition: if the random value is less than 0.5, then I'm going to set the group for its primitive to a open. Okay, and then going back to the primitive node and set the source group to open, so that the group which has primitive which has the group called open will get open with this primitive, and the one without the open group is kept as closed primitive. Now what I'm gonna do next is to use the VEX code to modify its conditions. If it's opened, then I'm going to make it back to closed geometry, and if it's closed, then I'm going to make it open by modifying the primitive intrinsic called closed. Okay, so let's do that by creating another primitive attribute, primitive wrangle, and let's name this closed. And first of all, I'm going to get the current conditions, current closed conditions, by accessing to a primitive intrinsic, just like we did for the measured area and measured volume. So in this case, it's going to be an integer value, so I'm going to create an integer variable named closed and use prim intrinsic named as closed at prim num. Okay, now we can check if if each of the primitive is closed or not by checking if this closed value is equal to 0 or not. So if closed is equal to 0, which means it is open, in that case I would like to make it back to a closed value, meaning I need to set this primitive intrinsic named as closed to 1. To do that, there's just a function for it in order to modify the primitive intrinsic attribute if it's writable, which is called as setpackedtransform. Okay, and if you look at the parameters, you have a total 4 parameters. First one is the geometry input number. The second one is, the geometry handle, so it always going to be 0. The second parameter is the name of the attribute, in this case a closed. And third one is a primitive number, so the same as prim num. And then finally the value that you want to set, in this case an integer value. So first one is 0, second one is closed, third one is prim num, and the last one is the value that you want to modify. And in this case, if it's closed, if the closed value is 0, then I want to make the closed value into 1, so that the opened polygon will be closed, and see what happens. And you can see that the whole geometry has been closed back again. Now if you want to make it open for the closed one, then you can create another condition called else and set prim intrinsic 0 closed at prim num 0, which makes the polygon open. Okay, so if you go back here, previously the one that has been closed become open, and the one that was open become closed. So this primitive intrinsic is pretty useful when you need to go back and forth the condition for the polygon whether it's being closed or not. You can also use this to convert the polyline into a polygon or polygon into a polyline. So that's how you can override the intrinsic value when it's writable. Now the next thing I would like to show is the primitive intrinsic values called typeid and typename, which can be used to check the geometry type you're currently using. Now going back to the first examples, by having all these different types of geometry, each of the geometry has different kind of types. By going into the primitive intrinsic and check two attributes types, which the first one is called as prim type ID and type name. Okay, and if you click the polygon, let's also hide the other one, the closed. So if you look at the polygon type, it says the type ID is equal to 1 and the type name is equal to poly. So you can use these values to indicate what kind of types of geometry you're actually dealing with. If you click at this one, which is the mesh type, which has an ID called 4, the name is called mesh. This one, 5 nerves mesh. This one, 20 volume, BDB 23 BDB. Sphere is 9 and sphere. And the packed geometry is 24 and packed geometry. So as you can see in Houdini, there is tons of geometry types for the primitives, and each of the primitive type geometry has different intrinsic attributes, like I just showed. And these values are sometimes used for in VEX by using it for some conditions. When you have a polygon, then do this. When you have a mesh, do this, and something like that. So let's see some simple example to use this values. Let's first create a grid. Let's set the size to 2 by 2. And also the column rows and columns to 2 by 2 as well. Make it a really simple grid shape. I'm gonna copy it 2 times, 1 and 2, and move this to a side to the X direction for the second grid. I'm going to move this to X direction by 3, and for the third one, I'm going to move this by 6. Okay, and I'm going to merge these together. Yes, and each of the grid, I'm going to change the type. So the first one, I'm going to change it to polygon. The second one, I'm going to change this to a mesh. And the third one, I'm going to change this to a nerves. So I currently have 3 different types of primitives being stored inside this merge node. By clicking this merge node and going into the geometry spreadsheet, and if you have a type ID and type name being shown from this drop down menu, you'll be able to see a type ID 1, 4, and 5, and the poly, mesh, and nerve mesh for the type name. Now based on those values, I can create a different behaviors using VEX code. Let's try to do that. I'm going to create a point attribute, a point wrangle, so that I can modify each point for each primitive. Let's name this type ID and type name. Oops. And first I'm going to start by getting the primitive for each of the point by using a function called point prims. Now point prims will give you a list of primitive which is attached to a point, but each of the point has only one primitive in this case, so I'm going to just retrieve the first one from the array as a single item. From this primitive number, I'm going to retrieve the type ID from the primitive intrinsic attributes using the prim intrinsic function. So int type ID is equal to prim intrinsic 0 type ID prim. And this should gives you a type ID for each of the primitive, for each of the point. Now, based on the type of this ID, I'm going to change the behavior of this point. I'm just going to change the movement, how the point should be moved for each conditions, each type ID conditions. So let's say if type ID is equal to 1, which means it is polygon, then I am going to move each of the point y direction to a specific a parameter values using a channel call value. So I'm going to promote this one by clicking this button here. So now I can move this, and you see that only the first one is moving, only the first grid is moving. That is because this has an ID is equal to 1. If you go to the geometry spreadsheet, and this first primitive has a type ID is equal to 1, so that's the one that can be only moved using these conditions. Okay, so let's say, so the next one is the type ID is equal to 4, which is the mesh. So else if type ID is equal to 4, then this time I'm going to move the y direction to a negative val parameter. Now, like this, and you now be able to split all these 3 values with different conditions just by using a type ID. So there might be a time you might have a different types of geometry contained in one node. So in that case, you can use this kind of conditions. You can use this kind of primitive intrinsic with the type ID or type name to check to modify the specific geometry type with this kind of conditions. If you go back to the geometry spreadsheet and look at the type ID and the type name, you can see that these are read-only grayed out, so you cannot, for these ones, you cannot modify these values by yourself. Now that we have seen a bunch of primitive intrinsic values and how we can set the intrinsic value if it's writable, next thing I would like to see is the special intrinsic attributes for the type called packed geometry. And specifically, I'm going to look at a transform intrinsic values, which can be used to change the transformation of this packed geometry. If you go to the description page for the packed primitive in documentation page for the Houdini, it explains it as an instance of a template geometry, which is used to reduce the memory if you need to duplicate the same geometry over and over again, which makes the calculation faster. The downside of packing the geometry is that by packing the geometry, you cannot access to a single point information or vertex information anymore in order to modify each of the point with specific functions. But instead, you can use a transformation for whole packed geometries for translation, scaling, and rotation by accessing to a specific intrinsic attribute of this packed geometry. So let's try to do that. First, I'm going to create a sample geometry like rubber toy and use a pack node to pack this geometry. So by packing the geometry, you'll be able to convert this into a single point, single primitive, single vertex, and packed geos. So all of these number of points and primitives and vertices has been packed into one primitive, one point, and one single vertex. These. And for the point, it has the position information of this packed geometry, and which is also equivalent to a pivot position of this geometry. Pivot means is a a rotation center, a scaling center of this geometry. And for the primitive intrinsic, you have, let me also hide this intrinsic, and you have several transformation related values. And most of the cases, what you use is this transform one, and also a pivot attribute. So for the pivot, it is equivalent to the point position right here, which is the center of this geometry. But you can also modify this. As you can see, this is writable. For the transformation, this is a 3x3 matrix which contains the information for the rotation and scaling, which is also writable. So you can modify these attributes to actually control the size and scale and the rotation of the geometry, and also change the pivot, as well as changing the position by accessing to a point attribute of this geometry. And there is several ways to access to this intrinsic attributes for the transform and pivot, and to do the transformation. I'm going to show you one by one. The first method that I'm going to show you how you can transform this packed geometry is to use the same a function that we have been using, which is the prim intrinsic function and set prim intrinsic attribute function. First, I'm going to create a primitive wrangle, and let's start by trying to move this geometry, packed geometry, which is pretty simple. You just need to modify this point attribute. Okay, so I'm gonna name this transform with intrinsic. Okay, so first of all, I'm going to create a directional attribute, directional variable to move this toy geometry. So let's start by creating a vector direction, then set, and I am going to create a x coordinate which is negative CHF x and 0 for y and z. Let's promote this x value. Let's change the range from 0 to 10. I'm going to try to use the matrix in order to do the translation, the transformations. So first I'm going to create a matrix, starting from the identity matrix, then use the translate function to translate the matrix, 4x4 matrix, using this direction. Let's also change some values for the x. Now what I'm going to do now is to modify the point position of this packed geometry, but currently we are in the primitive wrangle. So first of all, we need to retrieve the point number for this primitive. So in order to do that, I'm going to first create a prim point variable, and then use the function called prim point. And you need to input 3 parameters to retrieve the point number from the primitive. First one is the input number, second was the primitive number, and the third one is the vertex number. So since we only have 1 point, the third one will be 0. So 0 prim num 0. Now that we have a point number, we can get the point position, accessing to a p attribute at prim point. Now let's try to modify this point position using the matrix by multiplying the point position by this matrix. Then we can update the current point position by using the set point attrib 0 p prim point with the updated point position. Okay, I think I should make this point. Now the rubber toy has been moved, and you can check that by changing the slider values here. So you can see that by changing the point position, it's changing the whole geometry position. So the point position indicates the translation values for this packed geometry. Now next, let's try to do the scaling and rotation. So as we did for the matrix sessions, the order of the transformation matters, right? So if you do scaling, translation, rotation, or translation, rotation, scale, the result becomes different. So that's one things you need to remember about, to be careful of. And also when it comes to a scaling and the rotation, the pivot, the center point position for the scaling and rotation also matters. And for this primitive intrinsic, you can actually get the default pivot values by accessing to this pivot intrinsic attributes. So let's try to get this pivot values first and use this as a rotation center and scaling center. Okay, so first of all, I am going to retrieve the pivot, which is the vector value. So let's name this pivot vector variable and access it in from a prim intrinsic 0 pivot at prim num. Now let's try to do the rotation first. So in order to rotate, we first need to move the geometry to the 0, 0, 0 coordinate, and currently the geometry is at this pivot coordinate. So the first thing you might want to do is to, before doing anything, translate the whole stuff to a minus pivot position. Then after translating to the direction, I can use the rotate to rotate the matrix with some angle values. So let's also create a angle values like float ang by multiplying the attribute, the parameter which could be from 0 to 1, multiply by pi, multiply by 2, so that the value will be in between 0 to 2 pi, meaning in degrees, which is equivalent to 0 to 360 degrees. Now I am going to use this angle for the second parameter to rotate the matrix, and for the third parameter I need to set the axis. So let's say y-axis. Okay, now after doing all the translations, I need to move back the whole geometry to the pivot positions. So translate mat pivot. Now let's promote the angle value, angle parameter right here. And let's check what's going to happen by changing the angle. Now currently you do see a rotation transformation, but only for the point. So the point position is moving, is rotating based on this matrix, but the actual rotation for this single geometry is not happening. So what you want to do is to do the same. You want to use this same transformation matrix to rotate this geometry itself as well. And you can do that by accessing to a primitive intrinsic of this primitive called transform, which we have seen right here, which is also writable. So let's try to do that. First of all, I'm going to retrieve the current transform values, which is the matrix 3 variable attributes from the primitive intrinsic. So matrix 3, let's name this current mat is equal to prim intrinsic 0 transform The reason why it is 3 by 3 matrix is because this only contains the scaling and rotation transform information, and it doesn't contain the translation information, which is because the translation is done with the point. Okay, and prim num. Now that I have got the 3 by 3 matrix, which contains the scaling and the rotation, I can now modify this current mat by multiplying it with the matrix that I have created. Now, since this matrix is 4 by 4, which also contains the translation, I need to convert this into a 3 by 3 matrix in order to be able to multiply with the 3 by 3 matrix. To do that, you can cast it like this, creating a parenthesis with a matrix 3. For the matrix 4, you'll be able to convert the matrix 4 into a matrix 3, so that you can only retrieve the scaling and the rotation part from the 4 by 4 matrix. Okay, now that I have modified the current matrix, let's set this current mat as a new matrix value for the intrinsic transform attribute. So set prim intrinsic 0 transform prim num with the current mat that I have just modified. Now the geometry has been rotated together with the point, and if I change the rotation, you see that the geometry is rotating as we expect. So this is how it works with the primitive intrinsic, especially for the transform. Okay, I think I missed it. It has to be prim num. Okay. Right. So let's add another transformation which is a scale. So I'm gonna make the scale coming before moving into the x direction. So somewhere right here. So scale mat. Let's create another parameter set. So for the scaling, I'm going to create another parameter that's called s, using chf scale, which is going to be 0 to 1, and use s for x, y, and z coordinate for the scaling transformation. Now promote this scaling parameter, and you can see that the geometry is changing its size by changing this slider values for the scale. If it's 0, it just disappears. If it's 1, keep the original size. If you increase it, you can keep it bigger. All right, so works as expected. So this is how you can use the intrinsic attributes, especially for the transform intrinsic attributes, to modify the transformation for the packed geometry. Now you can actually do the same thing, same transformation, but in more easy manner using some specific function for the packed geometry, which is called as packedtransform. So let's see how we can use that. I'm going to create another primitive, or I'm just going to copy this primitive wrangle that I've created and rename this to a packed transform. Okay, and what I'm going to do is, instead of using all these calculations here, modifying the point position of the packed geometry and also modifying the intrinsic parameter of the geometry separately, I'm going to delete it all and just use a function called packedtransform. And for this one, you need 3 input. One is the input number, in this case 0, and the second one is the primitive number, which is in this case a primitive prim num, and the third one is the matrix, 4 by 4 matrix to transform, in this case a mat. So by using it, 0 prim num and mat, you actually get the same result that I did right here, accessing to a primitive intrinsic like these. It's just this function does do the same job accessing to a primitive intrinsic inside this function and just do the same transformation. So as you can see, this is much easier. So most of the cases, you don't really need to access into a primitive intrinsic, but except for this pivot, but you can actually just use this packed transform to modify the intrinsic transform attributes to transform the packed geometry, which is pretty easy. The reason why I showed the hardcore way first by accessing to the primitive intrinsic is because I wanted to show you that the packed transform is actually accessing to the intrinsic attributes for the primitive. I just wanted to show you that. So if you want to have more customized transformation, you might want to go back to this way to do more complex transformation, but most of the cases using this packed transform function just works fine. Now actually there's one more function in order to transform the packed geometry, and I would like to show you that one as well, which is called as setpackedtransform. So let's see that. I'm going to copy this node again, and this time I'm going to name this setpackedtransform. This time what I'm going to do is to make this packed transform renamed to setpackedtransform. And you might be able to see some difference between the packed transform and setpackedtransform. If you look carefully, before it was at this position. The y coordinate for this geometry is a bit upper. But if I use the setpackedtransform, it goes down. The reason for this is because for the setpackedtransform, actually the center of the transformation is already at the pivot for this function, meaning you don't really need to use this first translation and the last translation to move this whole geometry to the 0, 0, 0 coordinate, but actually the geometry, when you use this setpacked transformation, the original geometry is already placed on this 0, 0, 0 coordinate by using it. So if you comment these out, you'll be able to get the same result as the second one, the packed transform. Sorry, one mistake. You kind of need to translate back to the pivot position after doing the rotation. The rotation center is already on the 0, 0, 0, which is at the pivot position, but you actually need to move this back to the pivot if you want to keep it as at the original position. So you have to have this translate pivot on the last for this transformation to be able to have the same coordinate as the packed transform. So back up again, and if you compare with the packed transform and the setpackedtransform, you see that the position is now at the same position. So the difference between the packed transform and the setpackedtransform is only this first line, if you have this first line or not. For the setpackedtransform, the pivot of the rotation and the scale is already at the 0, 0, 0, so you don't need to translate the whole geometry with this. But for the packed transform, the center of the rotation for the packed geometry is not equivalent to the pivot location, but it's offset by the pivot direction or pivot distance. So you need to have this if you want to make this the pivot as the center of the rotational scaling. So both of them are useful if you want to start doing the transformation from the pivot location using a setback transformation. Make more sense if you want to use the global 0, coordinate for the transformation center, then using the packed transform makes more sense. And for this setpackedtransform, there's actually a function in order to retrieve the packed transform, which is called as getpackedtransform, which can retrieve the 4x4 matrix values for the packed geometry, equivalent to this setpackedtransform value. So let's try to see if we get the same values as this one right here that I have just applied to this packed geometry. So first of all, in order to check, I'm going to create a 4x4 matrix attribute called mat1 and store this matrix that I've created to this attribute. Let's check this out, going into the primitive attribute. So I have this mat1 4x4 matrix and let's also hide all these primitive intrinsic. Okay, so until 15. Now let's create another primitive wrangle to use a function called getpackedtransform. So primitive wrangle, name as getpackedtransform, and then retrieve the 4x4 matrix called mat using getpackedtransform 0 at prim num. Okay, so what I want to do is to compare this value with the value that I have stored previously using a setpackedtransform, and if it's the same or not. So I'm going to create another 4x4 matrix attributes named as mat2 with this mat. And let's compare these two values going into the geometry spreadsheet and looking at the something like mat2 14 values. Currently it says 0.2 minus 2.88. If I go to the mat1 14, which is right here, and you see that you have the same values here. So you can guess that the matrix 1 and matrix 2 is the same value. So you can actually get the equivalent value that you have set as a matrix for using the setpackedtransform by using a getpackedtransform. So whenever you need a transformation information for an packed geometry, you can use this function. Now, having all these information combined, let's try to do some practice using this packed Now, having all these information, let's try to do some exercise to try to use this transformation for the packed geometry for more practical usage. Okay, so what I'm going to do is to try to create a procedural explosion for the Voronoi fracture geometry. So first of all, I am going to create a base geometry starting from a box. Okay, and I'm going to create a bunch of points inside this box using, first of all, I'm going to create a volume using iso offset, and then use a scatter node to create a bunch of points inside the volume. Let's keep it like 100 so that we can have 100 cells. Now I'm going to create a Voronoi fracture node and connect the first input with the box and second input with the point. Now using this default parameter set, if you go to the primitive for this Voronoi fractures, you have this name as a name of the piece. So let's pack this each of the cells using this name as a guide. So let's use the pack node to pack this Voronoi fracture based on the name attribute by checking this name attribute here. Now I should be able to have 100 cells, each being packed, each primitive being packed differently. Now to be able to see the differences for each cells, I'm going to color it with different colors using color node with random attributes or random values. I'm going to set this to primitive, then set this to random so that each of the cell has different colors. Now what I'm going to do now is to create some animations so that this box will be exploded from the center so that each of the cells go outward and also rotating and moving to the outward direction. In this case, we don't actually need a scaling, so let's try to have a translation and the rotation transformation and use it for the packed geometry. So I'm going to create a primitive wrangle and let's connect it right here. And also I am going to name this as explosion. Now first of all, let's retrieve the frame related values, which is this value here. And let's first, and I would like to retrieve this value from 0 to 1 so that it'll be easier to use it inside of VEX. So first of all, the frame itself, the integer frame values can be retrieved by accessing to a @frame, a global attribute value, and by dividing it by a end frame values, which you can retrieve by accessing to $f_end, you'll be able to retrieve the value in between 0 to 1. But actually the frame starts from 1, so let's subtract this frame by 1.0, then divide it by f_end, so that we'll be able to have a value in between 0 to 1. And if I play it, you'll be able to animate this one from 0 to 1 based on a frame. Now next, I would like to get the pivot for each of the pivot location for each of the primitive. I use from the primitive intrinsic attribute. So vector pivot prim intrinsic 0 pivot prim num. Now what I want to do is to rotate each of the cells using the pivot as a rotation center. Okay, so let's try to do that. So if I want to use the packedtransform function, I need to move the geometry to the negative direction with negative pivot value, and then rotate and add this pivot back again as a translation. But if you want to use the setpackedtransform function, then you don't need to do the first operation. You don't need to move the geometry itself because it is already placed on the center, but you need to add this pivot as a last translation. So either way is fine. Let's try to use the packedtransform node in this case. So in that case, first thing I need to do is to translate each of the value, each of the node to the center. So using translate, and I also need to create the matrix. Start with an ident, then translate mat minus pivot. And let's try to see what's going to be the result with just this translation, okay? And let's also use the function called packedtransform 0 prim num mat. Now you can see that the whole geometry has come to the center using the pivot as a center value, a center position. Now, if you wanted to use this setpackedtransform, then this first pivot movement is not necessary. I'll just do the same things by using the ident matrix. Just move the whole geometry to the center, and the pivot location will be the center of the primitive. But in this case, I'm going to try to use this packed transform instead, right? So in order to make this back to the original position, you need to have another one on the last, which is the plus pivot translation, so that it will go back. In between, you need to do a rotation. You need to have a rotation so that the geometry will be rotated using the center point as the rotation center or rotation axis center. Okay, so let's rotate the matrix in between these pivot translation. And for the angle, let's create some angle value, shall we? So it might be better based on the frame values right here. So let's say f multiplied by some integer values. So int chi ang, and maybe multiplied by pi. Okay. And for the axis, it's better that we use the random axis for the rotation, I think, in order to make it a bit more natural. So to make a random direction, the one that I always use is to first normalize, and then inside I'm going to use the function called sample uniform or sample sphere uniform. And then for this parameter, I'm going to set the random using p as a seed, which will create a random direction in 360 degrees. Well, I mean 360 degrees direction. Okay, now it should do the job. Let's promote the ang parameter. Let's set it to 2 or 3 and start from the first frame. And if I play it, you see that each of the primitive now is rotating based on using the center of this geometry, which is the pivot location as the center of the rotation, and rotating with the random axis with this angle based on the frame. The next thing I would like to do is to move each of the cells or each of the fractures to a outward direction using translate. So let's do that. So the order of the translation could be after the rotation. After you have rotated, you can move to the outward direction. So let's do this after I have done all the translation, all the rotation. Then create a vector value to use it for the translation going outward. The direction that I would like to choose is, let's say, the normalized direction for the retrieve from the pivot. The pivot is currently the location, but if you want to go from the center to the pivot direction, then normalizing the pivot just makes the direction that you need. Now, I would also like to set the distance, how far it should go. So I'm going to create another integer attribute called chi dist. Okay, and also multiply with the f value so that it is related to the frame values as well. Okay, make this back to 0. 1, and then let's use this directional vector to translate this matrix. So to do that, you can use translate mat dir. Okay, now let's try to we need to promote the distance. So let's set it to something like 4. And let me zoom up a little bit, zoom out a little bit. Then let's play and see that each of the cell now is going outward as well as rotating. All right, so that looks good. Now, to make it a bit more natural, let's try to set the distance of each of the cells, how far it should go with the different random values. So currently all the cells is going with the same distance, but let's make it a bit different by multiplying this distance or changing this distance value with some random values. So I'm going to create another float values mult, and first of all I'm going to create the random values based on some random seed value, and the random value will create a value in between 0 to 1. So I'm going to use the fit function to remap this from 0 to 1 to, let's say, 0.5 to 1.0. And then I'm going to multiply it to this direction, which will maybe from 0.2 to 1.0, which will differentiate the total distance, how far each cell should go outward, which makes the animation a bit more natural, I guess. So this is it for today's session. This session is about the intrinsic attributes. I showed you what these are and how you can access it, how you can modify it, also how you can control the packed intrinsic attributes as well to change the transformation. Except for the packed geometry transformation, there's not much of a case you use this primitive intrinsic attributes or detail intrinsic attributes, but in some of the cases it is pretty useful. So knowing that you can have this kind of information is important. And I hope you found something new from these sessions. Now, thank you for watching. And next topic is a basic of random, how you can use random with several examples. What can it be used for? If you liked the video, I would appreciate if you liked the video and subscribe to the channel. And also, I have also started the Patreon page for myself. You can go to the page from the video description page from this YouTube. So if you would like to support me, I'd really appreciate it. Okay, thank you very much and see you next time.